you would be back to a straight line. So only certain fractions, and things like 3/7, 4/9, 5/9, 4/7, 3/5, 2/3, 5/7, they're nearly all some number divided by an odd number on the denominator. Not quite all of them, and I'll mention the exception later, but they mostly have odd numbers on the denominator. And so the question we want to ask is, what's going on here? And in particular, why do these fractions appear and not others? This, it turns out, is a very, very hard question to answer. And the reason it's hard, you can understand by thinking back again in terms of these Landau levels. So when you're on this nu equals third plateau right here, what's happening is that you've filled exactly 1/3 of the states in the lowest Landau level. Okay? Now, there were lots and lots of states in the lowest Landau level, and let's say there's 10 to the 23 states in the lowest Landau level, and you have to fill 1/3 of them. So you have 1/3 times 10 to the 23 electrons, and you want to put those into the 10 to the 23 states in the lowest Landau level. There's a lot of ways to do that. Okay, you remember it's that choose function, right? P choose n. So it's 1/3 times 10 to the 23, choose 10 to the 23. If you calculate that, that's basically 10 to the 10 to the 23. It's an enormously large number, and that's the different ways of rearranging 1/3 of the electrons into this state. And somehow what must be happening is exactly one of those states is picked as being favored by the physics. Okay? And the question is, which state is picked and what are the properties of that state? So it's a very, very difficult question to answer. The thing that we've missed that picks one particular state over the other is the Coulomb repulsion between the electrons. So remember when we were talking about Landau levels, what we did was look at a single electron and quantize it, and then just assume that the states for multiple electrons was sort of that single one copied over. But we didn't take into account the Coulomb repulsion. So to understand what's going on here, we have to solve the problem of many electrons in a magnetic field, but with the Coulomb repulsion. Okay? So in principle, it's very easy. In principle, all we have to do is find the ground state of this Hamiltonian. So I've added two terms here. This is the thing we solved before, and it's a particle in a magnetic field, except now I've put n particles in the magnetic field. And n is going to be a large, macroscopically large number. Okay, say 10 to the 23. This term is the Coulomb repulsion between any two electrons. And then I've added this term as well. What this term does is it takes any electron and it wants to force it to sit at the origin. So you should think of there being like, it's called a trap, but you should think of it as being a potential where the electrons want to go and sit near the origin. Okay, it just squeezes them together. The reason we put this term in is because if you have n electrons on a plane that's infinitely large, there's no reason they can't just be infinitely far from each other. So we want to somehow squeeze these electrons together. So there's going to be a payoff. Firstly, the electrons are going to sit in Landau levels because of this. The electrons are all going to want to squeeze towards the origin as much as they can because of the trap. But then there's this Coulomb repulsion that is going to want to force them apart. And what we want to understand is what's the lowest energy state of this Hamiltonian. Okay? All right, so how can we do this? There's various ways to proceed. It turns out, well, we know how to solve this. We did that in the last lecture. And it's very easy to solve this plus this, it turns out. Basically, you just have the state in the Landau level that's closest to the origin. Okay? So if we ignore this, we can certainly find the answer. But it's all about understanding what this does. So we somehow need to find a way to solve this equation and take this Coulomb repulsion into account. Okay? And I mentioned this in the last lecture, but we have a way in physics where you can solve one problem and then add an extra term and see how the solution changes. And that method is called perturbation theory. So a very obvious way to proceed is to solve the lowest Landau level, add the Coulomb repulsion, and think of it as a perturbation effect on our first solution. That fails miserably. And it fails miserably because the number of possible states of 1/3 times 10 to the 23 electrons in 10 to the 23 states is 10 to the 10 to the 23. So you're doing degenerate perturbation theory with this huge matrix that's 10 to the 10 to the 23 times 10 to the 10 to the 23. Okay, no one knows how to do that. It's diagonalizing this matrix that's much bigger than the number of atoms in the universe. So we need to find some other way to proceed. We need to figure out a way to solve this equation and find the ground state. I should say you can solve it for 2 electrons, it turns out. There's an analytic solution for 2 electrons. But there's no analytic solution for 3 electrons. You can solve it numerically up to about 20 electrons fairly well, but beyond 20 you can't even solve it numerically. Computers just aren't strong enough. So it's a very, very hard problem. How are we going to solve this? And the way this happened historically is, I think, one of the most amazing things in physics. It was solved by a guy called Robert Laughlin. He's in Stanford University. And what he did was guess. Just guessed what the answer to this is. And this is his guess. So it's a very, very simple wave function. And his claim is that this guess is the ground state of that very, very complicated Hamiltonian. Okay, so let me just walk you through what's going on here. These are, it's a wave function for n different particles. And the particles are going to move in a plane, so each particle has coordinates x and y, and I've written the wave function in terms of the complex combination x plus iy. Okay. There's 2 different parts to this. There's this bit here, which I'll come back to, and then there's this overall exponential factor. If you look at the wave functions for electrons in Landau levels, they all have that exponential factor, so that sort of just goes along for the ride. That's just expected from the fact particles are in a magnetic field. And so it's really this that's the guess. Okay? And you can see it's a very, very simple guess. One of the things that's going on here, this is holomorphic. It depends on Z, but it doesn't depend on Z bar. And that you can show is a property of electrons when they live in the lowest Landau level rather than higher Landau levels. Okay, so he did this astonishing thing. He just guessed the answer to an unbelievably difficult problem. It turns out that when you check this numerically against a small number of electrons, it works very, very well. It's sort of 99.99% close to the true answer for a small number of electrons. It's almost certainly not the right answer in general. So if you have 10 to the 23 electrons, we're fairly confident that this isn't the true ground state. Nonetheless, he didn't solve a problem, he guessed the answer. He guessed the answer incorrectly, but everybody decided that was enough to win the Nobel Prize. So this is what Bob Laughlin won the Nobel Prize for. And the reason is that although it's not quite the right answer, it's got all the right features of the correct answer. And there's a lot of physics buried in this wave function, very surprising physics that turns out to actually be seen in experiment. So that's what I'd like to tell you about, is how you can extract various bits of physics from this wave function and other wave functions, and what it tells you about this system. Okay? All right, any questions about this? So this is a beautifully, it's a wonderful wave function because it looks so simple, it's very easy to write down, and yet it's unbelievably rich and subtle in what it's telling us. Any questions about where we've got to so far? Okay, so I claim that this is the wave function that describes, okay, Bob Laughlin claims this is the wave function that describes many electrons in one of those plateaus that's the fractional quantum Hall effect. All right, so what can we do with this? It turns out that there's something quite cute here. It's a very easy wave function to write down, but anything you want to calculate using this wave function is extraordinarily hard. And the reason is that when you calculate things using wave functions, remember, you want to compute expectation values of operators. So what do? You have wave function, dagger, operator, wave function, and then you integrate over the positions of the particles. But those integrations now are going to be in 10 to the 23 integrations over the different wave function, the different positions of particles. That's extraordinarily hard, and no one knows how to do the integrals. So it's actually very, very difficult to compute exactly anything using this wave function. But one of the things Laughlin did is give a bunch of tricks on how you can go about understanding the properties of this wave function. In particular, he showed how to map it to a statistical mechanics problem of two-dimensional plasmas where people have some intuition. All right, but let me just tell you what happens when you do this. Firstly, we can ask, what do the electrons look like here? Given this wave function, what's the density of the electrons? And even that's not obvious for the following reason. You might think this tells you that as the electrons move further away from the origin, the wave function goes to 0 very quickly. So just looking at that exponential factor, you might think the density of electrons looks something like this. Okay? Except this factor is kind of doing the opposite, because as soon as two electrons come together, the wave function goes to 0. So this factor is telling you there's a very, very small probability for electrons to be close to each other, but that's what you expect from the Coulomb force. The Coulomb force is pushing things apart. And the remarkable fact is if you compute the density using this, these two balance each other precisely, and the actual density looks like the following. So the density is constant, and then it drops to 0 very, very quickly. And it's constant over a disk-like region, and that disk-like region has this radius. Okay, so it's a little bit of a calculation, but from this you can show the density is actually constant on a disk, and then drops off exponentially quickly outside the disk. This is the size of the disk. It depends on the square root of n, the number of electrons. That's sort of what you would expect, because the area of the disk then goes as n, which is the number of electrons. Okay. All right. So this wave function actually describes a disk-like region that has this radius of electrons. And you can compute more. You can figure out, what are the electrons doing? Have the electrons formed a crystal? Do they sit on particular lattice points? Or are they smoother and more homogeneous? And again, it turns out you can figure this out, and the electrons are perfectly smooth. There's no crystal-like structure in this wave function. Okay. So the way to think about this is that this describes basically a liquid of electrons rather than a solid of electrons. It's not quite true. A better way of saying it is it describes an entirely new form of matter, and I'll explain why it's a new form of matter shortly. What else did I want to say here? Okay, that's good. You can, already from this, you can figure out what the filling fraction is. So you know what the magnetic field is? That's fixed. That's B. It sits only here. You know how many electrons you've got, and now you know the density of electrons because of this. So all of that allows you to figure out the filling fraction, meaning what fraction of the lowest Landau level is filled by these electrons, and it turns out the filling fraction is 1 over m. So what that means is this m here that sits, it's the one parameter in the wave function, that m there is related to the plateau that you sit on. So if I just go back, if m is equal to 3, it describes this plateau, and if m is equal to 5, it describes the 1/5 plateau, which you can't see. It turns out to be about here, but there's a 1/5 plateau, and there's also a 1/7 plateau, which is observed. So the first thing to say is this certainly doesn't explain all of these different plateaus. It only describes the plateaus that have fraction 1 over m. Okay, 1/3, 1/5, and 1/7. But there's something nice that we see, because this is a wave function for electrons. And electrons have to obey the Pauli exclusion principle, or more precisely, they have to be fermions. So if you exchange the positions of two electrons, the wave function has to pick up a minus sign. And you can see that this wave function is going to pick up a minus sign only if m is odd, rather than m being even. So this is quite nice. It means that we know already that because the electrons are fermions, you're only going to see quantum Hall states like this when m is odd, not when m is even, and that is indeed what's seen in the experiments. 1/3, 1/5, you never see 1/2, and you never see 1/4. So already we start to understand something. We start to understand why only the odd numbers are appearing in these quantum Hall plateaus. All right, any questions about this? Okay, so this is the state that describes the ground state of those systems. Let me tell you a little bit more. Bob Laughlin not only told us the ground state, he also told us the excited states. And this is where things become much more interesting. So we know that we have this disk of electrons, this fluid of electrons, and now we think about what happens if you try and excite it. And there's a very obvious wave function you can write down. Again, it has very good numerical overlap with the true wave function, which is you take what you had before and you multiply it by this factor, where eta is a complex number, and eta is going to be the complex number that tells you where the excitation sits within this disk. Okay, so it's going to be the position of the excitation. All right. But by the way, I should say, it's a weird way to do physics, right? It's a weird way because usually in physics you have an equation and you try to solve it. And you'll see, sometimes those equations become so hard, there's no way you can do that. And so what you do is you don't solve it, you just guess. You just guess what the answer is. And for most people it just doesn't work, right? Because we always guess the wrong answer. But if you're really, really smart and you have the right intuition, it turns out it is a viable way to proceed and do physics. Bob Laughlin, it turns out, was just really, really smart. So this was his guess for the excited states. Let's have a look at what's going on here. Suppose you were to put m of these excitations. So there's an excitation at position eta, and if I was to put m of them together, what I would do is I would raise this to the power m, and then this factor looks very much the same as this factor. Okay? In other words, if I put m of these excitations together all at the same point eta, it looks as if I've just added an extra electron that's sitting at the point eta, because it looks exactly the same as this. Okay? But that means in particular that this object here should be thought of as 1/mth of an electron. All right, so that's a very weird thing. Electrons, we know, are indivisible objects. They can't be split. They're fundamental particles in the standard model. And yet, the claim is that in this liquid of electrons, the excitation that you can have is 1/mth of an electron. In particular, it carries the charge E over m, rather than a fraction of the fundamental charge in nature. So this is the prediction from this. In particular, when you're in the 1/3 state, so m is a third, the prediction of Bob Laughlin is that the excitation should be 1/3 the charge of an electron. So it's worth stressing how this happens. It's not really that the electron splits. What really happens is you have this liquid of electrons, and the liquid kind of moves apart a little bit and creates a little tiny bit of a hole, but that hole that's left carries a deficit of 1/3 of the electron charge. It's very similar to those holes that appear in band structure that we saw in metals, but now it's happening in this liquid. But it's true, you can measure this experimentally. What's happening is in this system, the things that are moving around and carrying charge carry charge 1/3 of an electron. And you can do experiments to test this. And in the 1/5 plateau, they carry charge 1/5 of an electron. So it's a very striking fact. You can somehow get fractional charge not by dividing things into smaller pieces, but somehow putting lots of things together and then letting them do funky, interesting collective things. With 10 to the 23 electrons can somehow make one electron split into 3. So it's a very strange property. All right. Any questions about this? Okay. This is weird. The objects that move around in this liquid carry a fraction of an electron charge. It's not the weirdest thing about them, though. So let me tell you what the really exciting thing is. They don't only carry fractional charge, but they also carry something called fractional statistics. So let me remind you about what you learned in quantum mechanics. Does everybody know about bosons and fermions? Anybody doesn't know about bosons and fermions? Okay. So we learn when we do first quantum mechanics that every single particle is either a boson or a fermion. And there's a little proof which I'll sketch on the board about why that is. And it turns out that proof is incorrect. That proof has a loophole. It's true in our world of three-dimensional space. Every single particle has to be a boson or fermion. But for particles that move only on a two-dimensional plane, it's not true. There's a loophole, and particles don't have to be bosons or fermions, but they can actually be anything in between. In fact, there's an even more dramatic generalization that I'll tell you about at the end of this lecture. So let me firstly remind you why we think particles should be bosons or fermions, and then I'll tell you what the very subtle loophole is that means they can actually be things in between. Okay, so what do we usually say when we do quantum mechanics? We consider a wave function for two particles, psi of R1 and R2, and we say that if we swap these two identical particles around, the wave function can pick up a possible phase. All right? The reason for this is that the particles are thought to be identical, so the probabilities have to be the same whether the particles are here or here, and probabilities are mod squared of a wave function. So the two things can only differ by a phase, and I've called this phase e to the I pi alpha. Okay. And then the next thing we say is, well, let's suppose we swap them, and then we swap them again. Then we have to come back to where we started from. So if we come back to where we started from, we swap them twice, we get this phase e to the 2i pi I alpha, but now this has to be equal to 1 because we're back to where we began. So what does that mean? It means that we have this equation here. The two solutions are alpha equals 0 or alpha equals 1. That's what we usually call a boson or a fermion. You swap them and nothing happens, or you swap them and you get a minus sign. And the essence of it is that if you do it twice, you have to come back to where you started from. Okay, that's the usual argument that we give for bosons or fermions. And it's a true argument in three-dimensional space, but it's not true when particles are restricted to lie on a plane. And I'll now explain why. It's a little bit subtle. The point is that if particles lie on a plane and you swap them around, it's called braiding. So what happens? This is space. I'll try and draw these pictures, and this is going to be time. So you have two particles, and when you swap them around, there's two different ways to do it. I can either do it clockwise, or I can do it anti-clockwise. Okay? Now, in three-dimensional space, those two options are actually the same, because if I do one, think about the world lines of the particles as things getting tangled. If I do one, I can always kind of change the world lines around and get them to look like the other in three-dimensional space. But in two-dimensional space plus time, there's an actual topological difference between winding this way and winding this way. Okay, if you think about knots, strings being tied in our world, the knots are different. There's no way that I can deform this picture into this picture without passing one of the world lines through the other. Okay, so there's this very subtle topological difference between the paths that the particles take depending on the way you change them around. And it might be that quantum mechanics of particles remembers whether you do this or you do this. And in particular, swapping them round twice, like this, involves this braiding of the world lines and doesn't necessarily have to give you back the same state as just this, where you left them unchanged. And that was the essence of the requirement that we have bosons or fermions when we... Oops. Okay, that doesn't work. All right. When we had bosons or fermions, we had this equation here. This equation is saying that when I swap them round twice, I have to get back... Oh, I pressed the wrong one. Silly me. I was wondering why it wasn't working. I think it's still good. Okay. This equation here says that when I swap them around twice, I have to get back to where I started from. If the particles are restricted to live in two dimensions, that doesn't have to be true, because swapping them around twice, you've braided or entwined their world lines, and so you don't necessarily have to get back to the same state. The system can have a memory of what you did. So that's the subtlety in 2 plus 1 dimensions. This was first noted, I should say, in the 70s by two, I think, Finnish guys called, I can't pronounce their names, Linus and Murheim, I think. And then in the early 1980s, it was rediscovered independently by Frank Wilczek, who's a Nobel Prize winner. And when they first thought about this, they didn't think there was any physical system that would actually have this. It was just mathematical games that, look, it's possible in two dimensions not to have bosons or fermions, but other things. And then some years later, it was realized that actually, in the quantum Hall effect, you actually do get these objects that are neither bosons or fermions. So there's a name for these objects. Objects that are neither bosons nor fermions are called anyons. And I think you're supposed to say it with an American accent. So anyons, the any means any phase. Not bosons or fermions, but anything at all. But if you're English, it's anyon versus any, and it's not. So, but if you're American, it's like anyon. So it sort of sounds a bit more similar. All right. So the claim is that in 2 plus 1 dimensions, the first claim is in 2 plus 1 dimensions, particles don't have to be bosons or fermions. They can be anything in between, where when you swap two around, you get any phase that you like. And the next claim is that the quantum Hall effect actually is a system that realizes this behavior. So these quasi-particles that have fractional charge, they also carry a fraction of the statistics of the electron. So they're not fermions, but they're a fraction of a fermion. That means in particular if you take two of these quasi-holes and you exchange them, you don't pick up a -1 or a +1, you pick up a phase, and that phase is e to the I alpha, where it turns out that alpha is 1 over m, where m is, the 1 over m is the same as the filling fraction, or the thing that labels the plateau. All right, there's a proof of this. The proof of this involves something called Berry phase. We came across Berry phase in the last lecture to do with topological insulators. It's a beautiful idea, Berry phase. I said then it's to do with connecting geometry to quantum mechanics. And it's really a beautiful idea that just keeps reappearing over and over again. And the way you do it here is you compute that same Berry connection, but now as you see how the wave function changes as you move one particle around another. So this is the key formula. It's the same formula we saw before, but before we divided by k, which was the momentum in the Brillouin zone. Completely different context, but it's the same formula that tells you something interesting. All right. This was a calculation that was actually done by Frank Wilczek in the late 80s to realize that these things are anyons. I should say that for 15 years now, there's been lots and lots of experiments to try and detect this. You should be able to see explicitly that these objects have fractional statistics, and no one's managed to do it. So it's quite a subtle thing. You can show they have fractional charge. The theory says they have to have these fractional statistics, but until now there's been no real experiment that shows that that's the case. All right. So this is where we are. The very simplest fractional quantum Hall plateaus are already interesting. The 1/3 and 1/5, they have excitations that have fractional charge and fractional statistics. There's now all the other plateaus that we also have to understand. So there's a long, long story about how to understand them. They're nearly all understood. They all have slightly different properties. But what I want to do in the rest of the lecture is just tell you about two slightly more advanced topics that have been interesting in the last couple of years about this fractional quantum Hall phase diagram. But any questions about particles with fractional charge and fractional statistics? Yes?
Are there any other experimental realizations of anyons?
Yeah, it's any system that has topological order.
I'm asking if they've been realized.
Yeah, I'm not actually sure. I suspect. See, the physics of topological insulators in 2+1 dimensions is basically identical to this. So I think that there are systems where people are fairly sure these objects exist. Whether or not they've been detected to have the fractional charge, that I'm less sure about. But I am pretty sure that there's been no experiment in any system to compellingly demonstrate that they have fractional statistics. But yeah, I think the topological insulators in 2+1, there are interacting versions, and I think there are materials that people think should realize these, and they should certainly have these excitations. Yes?
Are the anyons actual particles or imaginary?
No, they're actual particles in the system. But I should stress they're not fundamental particles. They're particles that emerge from the collective behavior of many billions of underlying electrons. We sometimes call them quasi-particles to distinguish them from fundamental particles. Another good example is what's called a phonon. If you build a lattice and you shake the lattice, there are sound waves, and if you quantize those sound waves, you get a particle called a phonon. And it's a real particle in the solid, but it's not a fundamental particle in our world. It emerges because you've built this solid. And these anyons are very similar to that.
The alpha for the anyons.
Yes.
Can take any value between 0 and 1?
Can take any value between 0 and 1. That's right.
Okay, so is there any connection between the lines of the work and the alpha? Because you showed us that there are two ways that we can that the lines can go in 2 dimensions.
Yes.
But how can that relate to any value for?
So what it really means, the key is that, maybe I should have put a third thing here as well. Exchanging them clockwise is different from exchanging them anti-clockwise, and is different from doing nothing at all. Okay? And is different again from exchanging them clockwise twice. So the number of times you wrap them, you might think that this state has to be the same as this state, but it's not true because you just remember, in principle, the quantum state can remember the braiding that it underwent through its history. So it's not so much that there's two, it's just that this is different from this, is different from this, is different from, and so on. Other questions? All right. As I said, I want to finish just by telling you about two very advanced topics. I'm not going to tell you many of the details, but I'll tell you sort of what people are excited about. And the first one I'm going to tell you about, people thought it was solved in the early 90s, and then about 2 years ago, there was a wonderful suggestion for how to really think about this. So let me tell you the story. This is this very complicated phase diagram. And remember what we expected classically. Classically, we expected that the Hall resistivity goes up constantly, and the other resistivity, rho xx, is a constant like this. Okay? And instead, what we're seeing is that the Hall resistivity goes up in jumps, and the other one goes up in spikes. Now, there's one region in this phase diagram that looks super boring because it looks just like our classical expectation. And that region is here. So you see here, there's a big bit where the line is perfectly straight. There's no plateaus. There's a plateau there and a little one there and one there, but there's a big region where it just goes up diagonally. And similarly, if you look at the other resistivity, it's more or less constant. Okay, it's got a little bit of a curve, but it's not spiking up and down. So naively, it looks as if this region here is the region which just agrees with our classical expectation, and nothing interesting is happening. And that couldn't be further from the truth. So in the last 2 years, I think everybody's been more obsessed with that region of the phase diagram than anything else. And I can sort of explain why in one word or one sentence. It's because if you look at the experiments, other experiments in this region, then you can show that the system has formed a metal. Okay. Now, we've seen what a metal is in previous lectures. A metal, roughly speaking, is something with a Fermi surface, some nice Fermi surface. And it looks very, very different from the Landau level structure that we've been seeing. And in fact, the experiments show something else. The experiments show that if you're at half filling, so the Landau level is exactly half filled, that's that region of the phase diagram, by the way. If you're at half filling, then the excitations about the Fermi surface are electrically charged, and they travel in a perfectly straight line, just like in a metal. So there's no Hall conductivity at all. Electrically charged excitations just travel in a straight line. Now, this is astonishing because, well, you can look at the axis down here. These are electrically charged particles that are in a magnetic field of approximately 20 Tesla. Now, I don't know if you remember strengths of magnetic fields. 20 Tesla is an enormous magnetic field. Okay, it's substantially larger than the magnetic fields that they use at LHC to bend these protons traveling at the speed of light. So they're in one of the largest magnetic fields that we can create on Earth, and yet these electrically charged particles are traveling in a perfectly straight line. But that's not what particles should do. They should bend. So somehow something's going on here where it's almost as if the system is shielding the magnetic field from these particles. And that's been a huge mystery for many years. Like I said, people thought they basically solved it in the early 90s. But 2 years ago, a wonderful physicist called Son, he's a Vietnamese physicist who now works in America, firstly pointed out there was things that people had missed, and secondly pointed out what he thought was a solution to this. And his solution is quite wonderful. And I won't tell you why it works, but I'll tell you what it is. Son suggests that at this half filling, the electrons, which are non-relativistic So the suggestion is that this is the third example that we've seen in these lectures where somehow relativistic physics emerges at low energies. We saw graphene, we saw topological insulators. Son's suggestion is that the quantum Hall effect at half filling is actually explained by relativistic physics. So he made that suggestion about 2 years ago, and lots of us got very excited about this, and there's been a huge amount of work last year in particular. And it's finally I think the dust has settled, and we think Son's suggestion is correct. It looks right. But to prove this is correct has been wonderful, involved wonderful interactions between different parts of the community. So in particular, there were people who were thinking about black hole physics, and it turned out that was useful to think about this property. And there were people who were thinking about very different areas of condensed matter physics, and that was useful. And there were people who were thinking about string theory, and that was useful. So in the last year, we've had conferences that have brought together people from black holes and string theory and condensed matter physics and all sorts of different areas, all because we care about this. And between us, somehow we had enough ideas to piece the story together. So I think it's been the most exciting thing in condensed matter physics in the last 12 months, certainly. But it's a nice example of how, and I've been stressing throughout these lectures, the ideas that are in condensed matter physics kind of stretch to particle physics and other areas as well. All right. Anybody want to ask me about something that I haven't given you any details about whatsoever? All right, let me tell you about the last thing. And this is currently the biggest push to understand fractional quantum Hall physics, because I think it's fair to say if we do understand it, this will revolutionize the world. So let me explain why. I'm going to tell you about something called non-abelian anyons. All right. Remember I told you that when you look at those quantum Hall plateaus, they're always a fraction which has an odd number on the denominator. And there's one exception to this. So here's the experimental data. And you can see amongst all of these, here's Landau level 2, here's Landau level 3. So this is a filled Landau level plus a partially filled two filled Landau levels plus a partially filled third Landau level. And there's a bunch of fractions that emerge. There's 7/3, there's 8/3, and right in the middle here is 5/2. And so this is striking because for the first time, there's an even integer on the bottom, but we've already seen a hint that electrons being fermions is the reason why there's only odd integers on the bottom. So already there's something interesting to explain here. So there's a long theory that goes into understanding this state. There's another wave function, which actually I could have written down. It's not too much more. It involves something called a Pfaffian, which is the square root of a determinant. But there's another wave function that we can write down that explains this, comparable to the Laughlin wave function. But the really exciting thing is what the excitations do. So the excitations have fractional charge. It turns out they have charge 1/4 of that of an electron. And again, it's been experimentally tested that that's true. But they're not bosons, and they're not fermions, and neither are they anyons in the way that I've just explained. There's something new completely, and they're new in a way that lots of people think is very exciting. So let me explain why. So you have this quantum Hall fluid at 5/2, and you can put in some excitations. So let's put in some number of excitations, and we'll call that number little n. So we're going to have these blue dots. The gray bit is the quantum Hall fluid, and the blue dots are the excitations, the fractionally charged excitations above the fluid. So we've got, each of them has charge e/4. And if you put in n of these objects, it turns out there's not a unique ground state for the excitations. Okay, so for n objects, there's several different states of these excitations, all of which have exactly the same energy. And the number of these states that have the same energy is 2 to the little n/2. Now it turns out n has to be even for a certain reason, so we don't have to worry about 2 to some fraction. So it's 2 to the little n/2. And what I want to convince you is this is a very, very strange number to be the number of ground states of n particles. Okay, so why is it a strange number? Sorry, that says 2 to the n points to it, should say 2 to the n/2. What's the easy way to get multiple ground states for some particles? Suppose each particle itself has two states. Each particle can have spin up or spin down. So one particle has two states. If you put in two particles, each of which can have spin up or spin down, you get four states. 1, 2, 3, 4. Glad I got that right. And if you put in three particles, you have 2 to the cubed states, and so on and so on. So if each particle can just have spin up or spin down, and you put in n particles, the number of states is 2 to the n. Okay? It's very easy to get that. Here, however, it's 2 to the n over 2. So how can you get 2 to the n over 2? Well, you can very quickly convince yourself that you can't get 2 to the n over 2 by each particle having its own individual property, like spin up or spin down. Okay? The only way to get 2 to the n over 2 is if somehow these particles are talking to each other and sharing that property between themselves. Okay? So what does this mean in particular? It means that, suppose that, so here's the four particles, and they sit in one of these states. So it's, the four particles have 2 to the 4 over 2, that's 2 squared, so the four particles have 4 different states that are shared between them. They can sit in one of 4 states. And suppose that I've only got access to this particle here. Okay? And there's no way I can see this. So I'm living in the red region. I can do any experiment I like on this particle, but I can't do anything on this particle. And I want to ask the question, which of these 4 states are my particles living in? Well, I've got no way at all of knowing the answer, because the properties of this particle aren't enough to determine what's going on. It's not like I can just measure a spin up or spin down or something. The state that the particles are sitting in is a collective property of everything that there is and does not depend just on this. And in fact, it's true. If you look at the wave function in this region, there's no way to tell which of the 4 states you're in. You can only tell if you patch together the wave function over the entire system. So this is interesting. This is interesting for the following reason. Quantum mechanics is fairly fragile, has something called decoherence, and if you take a quantum state and you make it interact with the environment, typically it loses all its quantum properties because of this thing called decoherence with the environment. But these states can't do this. So if, for example, a cosmic ray comes from out of space and it hits the red region, it can't deform the state of these anyons from something to something else because it can't know about the state of the anyon. The states of the anyon don't depend on what's going on in this red region. They only depend on global properties. Okay, so said another way, this is a quantum state whose information is spread everywhere in the system, is not compartmentalized, and if you nudge a little bit of the system, it's not going to affect the quantum state. So it's a way to protect quantum states against what's happening in the environment, make them much more robust than quantum mechanics usually is. Okay, so that's the first reason this is interesting. Somehow you get to store quantum states, but not store them as you would usually store information in some local region, but store the quantum states smeared over an entire region, and it makes them much more robust to error correction. Okay. You can think about the same thing with computers. If you have a computer, the information is always stored locally. It's stored locally in the hard drive, or it's stored locally in the computer itself. Imagine that you could genuinely store information smeared over all of space. That's what happens here. So it's something rather new. The next interesting thing is what happens if you move one of these states around another one. So, like I said, usually we're used to bosons or fermions. And I told you earlier in this lecture that you can now have anyons. Well, here there's something new entirely. So what's the deal? The n excitations can sit in one of 2 to the n over 2 states. So let me describe this by a vector psi that's dimension 2 to the n over 2. Okay, so if it sits in the first state, it's 1, 0, 0, 0, the next one 0, 1, 0, 0, and so on. Okay. And now what I'm going to do is some, like a magician with cups and coins. I'm going to sort of move these things around each other and then bring them back to where they started. So this is usually the case where you pick up pluses or minus signs for bosons or fermions, or as we now know, phases from anyons. Here you do something completely different. So if I take one of these quasi-particles and I move it in some path around the others, what happens is the overall state of the system doesn't come back to itself, but comes back to itself up to a unitary operator. So this object U is a matrix. It's a matrix that's 2 to the n over 2 times 2 to the n over 2. And for every path that these particles can take, you get a particular unitary matrix that acts on this vector. Okay. Now, this is what it means to do computation for computers. You put in some input state, and you find some way to do a calculation to output some output state. So this is the basis of what's called topological quantum computing. And the idea is that you create these anyons in the laboratory. The quantum information is smeared everywhere. It's not localized. And the way you do a computing operation is you do this and start shuffling these objects around. Your program gets translated into the way that you do the shuffling, and then the output is the quantum state that you have. And it's useful because it's robust against errors. You can do this, and because the quantum information is everywhere rather than localized, you don't run into the usual problems of errors. So there's huge activity at the moment by people like Microsoft, people like Google. They all have research teams who are trying to build these systems and use this in order to develop quantum computers. I don't know how far away it is, maybe 10 years, maybe 20 years. But when it happens, it's really going to revolutionize, I think, many things in our lives. All right. So I'm going to finish here, but it's just to say this complicated-looking picture is, I think, one of the most wonderful things in physics. And it's got so much interesting physics hiding in different corners of it. There's been 25 years so far in trying to understand what's going on in this picture. I wouldn't be at all surprised if there's another 25 years of interesting surprises waiting for us. All right, I'll stop there. Thank you for your attention.
So we have time for a few questions. That was a question? No.
That was Mitch.
On anything, actually, on the Kinesmatter lectures, they don't need to be about the fractional quantum Hall effects.
So you said that this band where we have, your lower line in this plot is basically flat, corresponds to half filling of the Landau level.
Yeah, half filling is...
But it's quite broad, that's what I'm wondering. So it has the same properties even though you're deviating a bit from half filling, or is it just at that point where it has those exciting properties?
What happens? As you deviate, you take that metal and you start... Let me answer it for a different filling fraction first, and then I'll go back to half filling, because maybe I'll remember the answer as I'm talking. If you're here and you start to increase the magnetic field, or I guess decrease the magnetic field, what actually happens is you start populating those quasi-holes, those fractionally charged quasi-holes. And this plateau here, we didn't talk about 2/5, is actually what happens if you have a 1/3 quantum Hall state with lots and lots of quasi-holes, which then themselves form their own quantum Hall state above the 1/3 quantum Hall state. Does that make sense? So the electrons form a quantum Hall state, then you get lots of quasi-holes, and those new quasi-holes form a second quantum Hall state on top of the first, and you can show that that gives rise to this. And then this one is what happens when the quasi-holes of the quantum Hall state form their own quantum Hall state on top by scanning. Oh, no, good. I do remember. Sorry, let me, because now I remember. Okay. At a half, I said that those electrons, it looks like there's a metal, and the charged excitations look as if they move in a straight line. Well, they do move in a straight line. Okay. As I shift the magnetic field here and here, what happens is those electrons bend as you would expect in a magnetic field, but in a magnetic field that's totally tiny. It's not 20 Tesla. It's the difference from the half filling to here. So all along here it looks like a metal, but in a magnetic field. But a tiny magnetic field that isn't 20 Tesla, but is the difference from half filling to there. Yeah, good. Okay.
Other questions? Okay, I have one actually. But so at the half filling, you said it was a metal, but does it have a Fermi surface like the other metals you discussed?
Yeah, it absolutely has a Fermi surface. Yeah,
okay.
round Fermi surface.
Around, so it's completely like a metal. Okay.
Yeah.
Okay.
And actually, it follows it from Son's duality that it's like that. But a Fermi surface for Dirac fermions,
right?
Not for normal fermions. So in particular, it has. So this is. So I don't know if you remember, but the spin of the fermion is the same as the momentum.
Right.
So it has this thing called spin Fermi locking, and you can. This is really the signal that you can use to check that this is correct.
And please pick up an evaluation. I should mention they're anonymous. You should not write your name on them. Just tell us what you think. So, honestly.
So how does it, the CFD enter in this?
So the very simple way, which is...
I guess I have to know.
this is a disk of possible stuff.
Right.
And one way to think about it is to describe flow energy physics described by Chern-Simons theory.
Okay.
From the wave functions themselves or from the Chern-Simons theory, you can see that on the edge there's a chiral mode. These chiral modes are cheated. And it is the CFT that is yeah. And now the astonishing fact is that if I take this CFT and I compute correlation functions, very high correlation functions, this gives me back a ground state wave function.
Right.
This gives me back a locked in simplification. Simplification is U1 to the n. So you can do everything in the CFT. And in fact,
this is some sort of video CFT.
Yeah,
Like,
yeah, very much.
So you know, you kind of have holography, like
Yeah.
the state of the moment.
Yeah, but there's sort of, because this is topological, there's no long wave length dynamics.
I see.
Nonetheless, it's really yeah, it's everything. And so all of these, these non-abelian anyons, this is all gradient not. It's actually understood in the CFT first, and then here, and then people. It's amazing. Totally amazing. And it's amazing because these things actually exist.
And then you can measure it. Good. Yeah. Yeah, it's not going to be in the morning. What's that? No, 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 no. Has to be anonymous. What's that? Yeah.
Wherever Mario wants, he's an expert. He knows these things.
The expert.
Where are we doing the picture? Here or outside? Outside.
You got a picture?
Yeah.
Yeah. stuff working today?
Sorry?
Is the tech stuff working?
I made a mistake, sorry. Yeah. Imbecille.
Yep. Okay, hello everyone. So welcome back. And we are about to begin the very last lecture of the school. Before we do that, let me just remind everyone, here's the schedule for the school. We are right now here. After this, we'll have a short break, and then the closing ceremony. And after that, there will be lunch. So let me emphasize, we're still all having lunch together if you want. The lunch tickets still work today. Okay, so we have Giorgio Paolucci giving us his last lecture on science at Sesame.
Okay, so good morning, everybody. It has been a pleasure to be with you all these days, and I hope to see you very soon also at Sesame. I hope that you will enjoy this last lecture, which is finally on Sesame. So this is our new logo, which has been you probably have seen our previous logo. The previous logo of Sesame was a UNESCO-style logo. Now it's more related to synchronization. And I don't know whether I said that before. Sesame is actually an acronym which stands for Synchron Light for Experimental Sciences and Applications in the Middle East. If you want to get information on Sesame with Google and you Google Sesame, don't forget to at least add the word synchrotron, otherwise you find all sorts of recipes using Sesame for as a spice, or you find a lot of information about Sesame Street, which was a BBC program in the 80s, and so on and so forth. So don't forget, if you want to get information about Sesame, Google Sesame and synchrotron at least. Okay, so just a reminder about what we're talking about, so that we've seen that before. A synchrotron light source is something which has an injector which produces the electrons, which are then sent into the storage ring, and then you get the beamlines. The beamlines is what we're going to talk mostly about, so these are the applications-oriented instruments which we have. We also said that a synchrotron light source, a synchrotron radiation source, produces a very wide spectrum, and we've been talking a lot about it. And we've said that because of this very wide energy spectrum, and because of the unique characteristics of the radiation which you produce with the synchrotron, it's a very powerful technique. We've seen examples in condensed matter physics. We've seen examples in cultural heritage. There are examples in medicine, in biophysics, material science, and you mentioned it. I always say that the actual limit to the use of synchronization is imagination, because it started as a physics-only type of methodology. But now we're addressing other communities, and sometimes we have to explain them, because if you talk to a physicist, a physicist will immediately understand what we're talking about when you talk about X-rays. If you approach an archaeologist, you should not give for granted that he knows, or he or she knows, what X-rays are. In any case, because of this characteristic of synchronization, there are a number of synchrotron radiation sources in the world. There is a map which is probably even old. There is the Canadian light source, As you can see, there is a high concentration of light sources in Europe and in far Asia. There is a project here in Armenia, and then there is one here in here. So this is the location of Sesame on Europe plus Middle East map. And if you zoom on it, you find out that we are very close to where we are now. So Ramallah is here. So this is where Sesame is. It took a long time to build Sesame. I don't know whether you know that, but the original idea dates back in the previous century. And as an institution, Sesame started it around 2003. So it's 14 years that Sesame as an institution exists. This is what the laboratory looks like now. We have a square type of building. Not all synchrotrons buildings are circular. Some of them are square. And it's located in a nice area about 35 kilometers northeast of Amman. As an institution, it is copied from its institutional framework is copied from CERN, so it has members and observers with the difference that if you go to CERN, you will see that a lot of countries are members and few are observers, while at Sesame is exactly the other way around. This is the list of members, which is unusual, as you can see, and the list of observers, which, as you can see, includes most of Europe and a lot of other countries, including Canada, Brazil, and United States of America, together with Russia and Japan. The objectives of Sesame are shown here. So there is an objective, it's a purely scientific objective, which is good science in the Middle East. There is an educational objective. There is trying to help in reversing the brain drain issues in the region, and give a contribution to mutual understanding. Now, Sesame is what is known as a third-generation lab. I remind you that we discussed the first, second, and third-generation laboratories. The original idea, which came in the late 90s, was to take a laboratory, an accelerator, which was going to be dismantled in Germany, and just reinstall it in the Middle East. This accelerator was called Bessie 1. Actually, it was called Bessie at the time, and then since they built a second one, they called it Bessie 2, so this one was called Bessie 1. And so the original idea was just to take this and reinstall it in the Middle East. It's interesting to note that this idea came out as a result of a big change in the political structure of Europe. You may have heard that in 1989 there was a change due to the fact that the Berlin Wall fell down, and so there was a process of reunification of Germany. There were two Germanys before, East Germany and West Germany, and so there was this reunification following this event in November 1989, and this had as one of the consequences of this was that the German government invested a lot of money in previous East Germany, and so one of this investment was the construction of a new synchronous radiation laboratory in what used to be East Berlin. So this one became available. However, BESSY 1 started its operation in 1982, so a long time ago, which means that it was built upon ideas which were developed around the 70s. Now, as I told you, one of the objectives we have with Sesame is to try to give some contribution to reverse the brain drain. And it's very hard to tell someone from the region who has gone to, say, United States with wonderful apparatus there, why don't you come back and use an instrument which is 50 years old? So that sounds a bit strange. So this idea was abandoned, and now BESSY 1, or parts of BESSY 1, are used to inject electrons into a larger storage ring, which is entirely new. So it's a new machine. This is what Sesame looks like. This is BESSY 1. So this is this is what in the original plan should have been Sesame. As you can see, the final project is much larger. This new storage ring has a circumference of 133 meters, so it's larger than some. It's of the same. It's about half of the synchrotron in Trieste. Is a little smaller than the Canadian Light Source. So it's a good lab. It's a good ring. And it can host up to 12 insertion devices, which are the undulator wigglers, which we've been discussing about during the first lecture. And then it has 13 bearing magnets 4. And okay, although we are using BESSY 1 as an injector, we are already thinking of a future upgrade to have a larger booster for something about micromolecular crystallography and something about the infrared beamline, which is on the other side. The building looks like that. As I said, it's a square one. This is the shielding, because of course these accelerators produce radiation. Actually, they are built to produce radiation, but you don't want people to be exposed to radiation for obvious reasons, because radiation is dangerous. Therefore, the accelerator is surrounded by about 1 meter concrete, both in the plane, which is the most dangerous, and on the top. The top is removable. This is a picture of the construction of the shielding, which was taken in 2010. So you can see all the workers. The side wall is fixed with opening for the beamlines, while the roof is movable, because you have to be able to access the tunnel to put component C. And this is what the experimental hole, or the inside of the of Sesame looked like in 2011. Doesn't look like that anymore, because all the space is filled now with instrumentation. The first, if you want, the first activity was in 2012, when the pre-injector was reassembled and produced the first electron beam in 2012. Then in 2013, basically the BESSY1, so most of the components of BESSY1 were reinstalled. This is what they look like. You can see here, if you look here, you can actually read BESSY if you look with some detail. So these are all components which are part of the German donation to Sesame, which have been reconstructed to have a booster. So this is the pi dipole magnet, this is the current monitor, cavities and corrector, and so on and so forth. So this was installed basically between 2012 and 2013, and then in 2014 the commissioning of the booster started. I was already at the Sesame by then, and the current, the specified energy was reached in September 3 years ago. And then here you can see a picture of the commissioning team who were very excited at the moment because they finally got an electron beam. These colleagues are all from the region. In particular, Maher et al. is Palestinian. We reported this event on our Facebook page, which I invite all of you to like. And this is the way I posted it on, as you can see, I posted it personally on Facebook, and we reached about 4,000 people in about a week, which was good. Yeah, so that was in 2014. Other things happened in 2014. For example, we had to build a new roof. As you probably remember, in 2013, this area was covered with snow. There was this huge snowfall in the end of 2013, which caused various sorts of damages, including the destruction of our roof. So when 2013, just as a personal note, at the end of 2013 is when I was asked to join the project. So that happened in November. In November they told me, okay, why don't you come and help us? And in December we had this accident, so I had a bit of a shock. But anyway, I came to Jordan and saw this, which is, you know, not very nice. That was in 2013. Anyway, we immediately acted. We contacted the company, and the old roof was removed and a new one was built. This is a picture which I took from the corridor out of my office in October 2014. Now, this is October 2014. I told you 5 minutes ago that the commission of the booster was in September 2013. So the commissioning of the booster was done under these conditions, which is a sort of a record. I think this is the only accelerator in the world which reached the specified energy without a roof. Anyway, so because of the new roof, we changed. You may still find this picture on the web, but this is the old roof. The new roof is a bit different. We changed the color to get a better. The color was changed according to try to have a better radiation heating insulation. So that's one thing. The slope has been increased to avoid accumulation of snow, and all the internal structure has been carefully checked, also with the intervention of experts from from Europe, in particular from Electra and from the Swiss Life source. Now, As I said, the beam, the storage ring is entirely new. The magnets were made, the construction of the magnet was supported by European Union with a project of of 2 million euros, which was coordinated by CERN. So CERN, together with our engineers, designed the dipole, the quadrupole, and the sextuple magnets. And then all the magnets were sent to CERN, and some of them were measured at CERN, and some of them were measured at other laboratories. And this is what they look like, dipole, quadrupole, and sextuple. And in
probably you have mentioned that, but I wasn't know about that. What's the strength of the magnetic field you use that to
the dipoles are 1.5 Tesla. So this is the first complete cell assembled at CERN, and that was the beginning of 2016. When and then okay, I think we can skip a few things, but then okay, let's put it this way. Then the components have been moved to Jordan and installed during last year, basically. Okay, this is the vacuum chamber. This is a picture of one of the RF cavities. The RF cavities are supported by Italy, which gave an in-kind contribution to Sesame. Okay, the cavities itself was 1.25 million euros. The total contribution from Italy by now is about 4.8 million euros. I'll say a few words about another technical contribution from Italy. And this is a picture taken last year of the first 3 cavities. The 4th one was installed I'd say in spring this year, and now all of them are installed on Sesame, and and they are being tuned. Okay, these are some details about the RF power plant. So we have a number of solid-state amplifiers, which is to get the power for the RF cavities. They have been designed by Soleil, which is a synchronous radiation facility near Paris. And so we got them, they were bought by Sesame. The first one was produced by Soleil, and the other 4 by another company. So going back to this picture, these are the main beamline which we're thinking of building nowadays. We will focus on the first 4 of these beamlines, which are under construction, and these are listed here. We try to give names which have a meaning in this region. So Basema is the beamline for absorption spectroscopy for environmental and material applications. It's a range of about 4.5 to 30 keV, and it is based on a donation from the Helmholtz-Zentrum Dresden-Düsseldorf, and it was installed previously at the European Synchronous Radiation Facility. However, we had to install a new infrastructure, including the X-ray radiation hatches, and we're going to have a new detector, a novel detector, which I will describe with some details. EMIRA is the electromagnetic infrared radiation beamline, and it covers, of course, a very low energy range. It's entirely new. It's being built in collaboration with Soleil, the synchronous radiation laboratory in France. And it requires some modification to the storage ring vacuum chamber. SUSAM is a beamline for material science, mainly powder diffraction. It's based on a huge wiggler with a magnetic field of 2.1 Tesla. And it is based on a donation from the Swiss Life source, and it has a donated detector. It's the first, I'm stressing this because this is the first donation we got from a company. And we are now working on the rest of the experimental station. And then we have a beamline for macromolecular crystallography, which covers an energy range around 10 keV. We are still working on the detailed specs of this beamline. This again an entirely new beamline. It's partially supported by the Jordanian Scientific Research Fund, and it's based on an in-vacuum undulator. So you remember the undulator? I showed you pictures of the undulators. Now to reach the energy, the wavelength we need for this thing, the only possible solution is that you put the magnets very close to the beam. In order to do that, you have to remove the vacuum chamber, so you have to put all the magnets under vacuum in order to close them and go very close to the beam. In the particular case of this beamline, the minimum gap is going to be 5 millimeters, so very, very small. And we can do that because we have a new storage ring. Now, some details about the beamlines. Yes, beamlines. So the first one is the X-ray absorption beamline. X-ray absorption, X-ray fluorescence. We have seen some examples. The painting by Van Gogh was an example application of a beamline similar to that. The beamline scientist in charge is Messaoud Arfouch from Algeria. And this beamline, as I said, is based on a donation from a German institution. This is what the beamline looks like. We have a monochromator here. This is the top view, this is the side view. This is the monochromator. So this selects one wavelength or one energy at a time. And before that, you put a vertically collimated mirror. So it's a mirror which takes the divergent beam from the synchrotron and make it parallel, because you want to have a parallel beam to select the wavelength. Then the horizontal focusing is done within the monochromator by bending the crystal. And then we have another mirror here. You see the side view, which focuses the beam more or less here in this scale, as you will see in a minute. These are the components as they were in a lab until 1 year ago, more or less, a bit more than 1 year ago. And this is what the hatches look like. This is a radiation shielding device or hatch, which contains all the components which I've shown you in a minute ago. And here you connect, you put a pipe which takes the radiation from here to the experimental station, which is here, which as I said, it's far away from the components. These are moments of the installation. So this is one of the mirror chambers moved from the lab inside the hatch. So that was done while the hatch was still open. And nowadays that is what they look like. Actually, This is an old picture. Now everything is connected and under vacuum. The monochromator has been tested, and because this is an old beamline, so you have to make sure that all the motors move the components in here carefully. This is Yazid Mohammadid from Jordan. This is Farouk Alumari, also from Jordan, electric engineer and electronic technician, setting up the movements. And because we have all these observers, we got help from a team from Soleil who came to help in the alignment of the various optical components. So these are, as a picture, this is, I think this is Messaoud Arfouch, this is technician, this is Taher, our alignment engineer, and these two guys are from Soleil. This is a technician from Pakistan who was working with us at the time. Now, as I said, Italy is contributing to the project, and another contribution after the cavities is the building of a fluorescence detector, a new one. This is a prototype. The new one is much more advanced. Anyway, this is a cyclone drift detector. This is one strip composed of 8 cells. Each of these cells can handle up to 50 kilocounts per second. So we're going to have 8 strips of 8 cells each. So we're going to have 64 cells, which will give us a rather large area, about 500, about almost 600 square millimeters, and will give us a very high counter rate capability, up to 3 million counts per second, because you distribute the counts. These are the pictures of this, the electronics. This is the first prototype, which gives good fluorescent resolution, 160 electron volts at 1.5 kilo electron volts at room temperature. Normally you have to cool down these devices. Okay, these are details which we can skip. And we start by having also a standard detector, so that we can start measurements even sooner than this novel detector, which is being done. I was in Trieste in June, and I checked. They are actually working on the prototype, and I saw the electronics. So I assure you that in a few months that will be ready. And we expect the beamline to be ready autumn this year. At the same time, Messaoud Arfouch is involved in scientific research activities. As I said, X-ray absorption spectroscopy can be used for quite a number of applications. And in particular, he was involved until 1 year ago, or until the beginning of this year, in a project supported by IAEA, the International Atomic Energy Agency, on soil contamination. Because once you can look at, if you can look at a small quantity of a paint in a painting, you can also look at small quantity of contamination in soil. So he actually did everything from getting the samples. So these are the collecting of soil samples at various various distances from the Jordan River, and also including some earthworms. And these are the results, which you remember we mentioned the difference between chromium-3 and chromium-6. This is an enlargement of the chromium-3, which I remind you is the poisonous one. This is zinc K-edge. These measurements were done at Elettra about 3 years ago, and these things have been fitted with standards, and the composition of the contamination was found out and identified as coming from some companies, some industries in the region. Okay, so that is the status of the activity at the beamline, Schaff's beamline, and we go to the other beamlines, and we go to EMIRA. EMIRA is the infrared beamline. The scientist in charge is Jihan Kamel from Egypt, and she is in close collaboration again with a French group in Soleil. And this beamline looks very much different from any other synchrotron beamline because if you remember, I showed you during the first lecture the angular dependence of the radiation emitted, and I told you that high energy are emitted in a very small angle around the electron orbit. But if you look at the drawing, you will see that higher wavelength or longer wavelength or very low energies are actually emitted at at much higher angles. And since in this case we are going to the lowest part of the spectrum, you want to collect photons at very high angles, and therefore you do that by putting a mirror very close to the storage ring. So actually the first mirror is here, and this is the bending magnet. Then the first mirror is put in this way, so it deviates the beam horizontally. Then you put a mirror like that, which brings the radiation up. Then you go through the shielding wall, and then you come back again. So it's a strange beam line. This is a top view of the thing. So that's what I told you. The first mirror is here, basically almost on axis with respect to the storage ring. So this is put like that. Then here you put something that brings the radiation up. Okay. As a result of this requirement of going very close to the storage ring, you get a very crowded area or space around the storage ring. That took us a very long time to design things in such a way that we were sure they would fit. And don't forget, I should stress that two technical groups were interacting one with the other, because this part has been designed completely by Sesame. This part has been designed completely by Soleil, and everything in between had to be designed together to be sure. It looks like a stupid thing, but really it's a very crowded part of the spectrum. I'll show you in a while what in reality looks like. So that is a view of the entire thing. This is the shielding wall. You have to make a hole. We have to make a hole through the shielding wall, and then this part is under construction now. But this part as most of this part has been installed, as you can see here. The picture is not very clear maybe, but here you see all the components. Here you see Jihan supervising the installation of this chamber, and this is the dipole magnet, and this is the extraction port, and then this brings, there is a mirror here, as I said, a mirror there, another mirror there that goes through the wall and brings the radiation to the experimental station, which we already have. This is the what the microscope, infrared microscope, looks like. It is not on this wooden table anymore. Now it's on a proper optical table, and it is already installed in its final position. This device has been used. It has an internal source as well, which can be used for characterization measurements, but which gives, of course, much less brilliance than the synchrotron radiation. But nevertheless, it has been used in 2013, so before I actually joined the project, a call for proposal was open, and these are the members of the review panel which had a look at them, and we had a number of users coming to Sesame from various regions, one of them being Sohaila Rehman from Pakistan. She came a couple of times, and they're writing a paper on the subject. Some papers have already appeared with the results obtained on the microscope, and I'm sure that others have been. There's a group from Egypt. They came as users after this call. This is part of, there was a proposal by Immaculada Martinez Rovira and Ibrahim Youssef, who used to be our binline scientist, but then he decided to go to Europe. And Ibrahim, I think it was a Jordanian Palestinian. Oh, well, he still is. He's still alive and healthy, but he's somewhere else, unfortunately. Okay, we have a number of collaboration. So this is a list of people who have been using our infrared, and these are some results which were obtained. And this is a duplication of what we saw before. This is one thing that happened. We have a number of programs to access existing laboratories that might be interesting for you. In this particular case, the one on the left is Ibrahim Yusuf. The mid one, the second one from the left, is from the Anders Engdahl, who is the infrared scientist at Max 4, and these two ladies are Randa and Enan, from the Jordan, from the JU, so from Jordan University. And they went together to Lund, so all the way to Sweden, and they performed some measurements there. We have a number of schemes to do that. By the way, one of them I will describe with some details in a while. For SUSAM, the material science beamline, the beamline scientist in charge is Mahmoud Abdelatif, also from Egypt. And he is redesigning this beamline, which, as I said, is a donation from the Swiss Life source. We have some components, some others have to be installed. He took care of designing the, he together with our engineering group took care of designing the optical and experimental hatches, which have been ordered in the meantime. These are This is the wiggler. We tried to install it on the in the storage ring, but then we have to take it out. But anyway, that is what the wiggler looks like. You can see the they're covered here, but these are the two sets of magnets up and down. You know everything about it. This is a strong type of device. These are the characteristics. Can go to a gap of 12 millimeters. You remember the K parameter? The K parameter in this case is much larger than 1, therefore we're really in a wiggler condition. And I would like to stress the amount of power this thing produces. This produces at the maximum current in the storage ring at an energy of 2.5 GeV, it produces a power of 6 kilowatts, which is of course an awful lot of thing, because it's an awful lot of power because it's concentrated in a very narrow angle. These are the type of emission you get at various gaps. And so since what this beamline is going to use, unfortunately, this is the trick about wigglers. Wigglers produce an awful lot of radiation, but most of the radiation is in this part of the spectrum where you don't want it. So actually what you want to do in this particular case, the energy is going to start at about 5 keV, so about here, or even higher than that. So you want to get rid of all this, which is somehow is a waste, but there's nothing we can do about it. And so we are, of course, this is a typo. This is after the filter. So we're going to insert a filter which is made of graphite, which will basically limit the minimum energy to between 5 and 7 kiloelectron volts. We are still discussing the type of filter. One idea is to reuse the solution that was used at the Swiss light source, which was a rotating cylinder. I personally don't like this idea, because if you put a filter of, so the idea is that you use a 1 millimeter thick graphite cylinder, which is rotating to distribute the heat. So if you do that, so you have 2 millimeters of graphite of attenuation. If you just do that, you get that this is the temperature distribution, the calculated temperature distribution, which reaches 1400 Celsius, which is something you don't want in your ultra high vacuum system. So we are thinking of other solution to reduce this number. Okay, these are details which I think we can skip. This is what the beamline looks like. Conceptually, it is not very different from the other one. Again, you have a collimated mirror, a monochromator, and a focusing mirror. So it's going to be very similar to the ones. These are details about the no, we still have 20 minutes, not 5 minutes. Wonderful. Just have a look. So these are the calculated spot the sample, which is going to be 2 millimeter wide by 300 microns high. So it's going to be very well focused with a divergence which allow to measure accurately any structure. The lead arches have been calculated, and this the beamline we think will be ready in spring next year. For macromolecular crystallography, we got special support from Jordan. of 1.5 million Jordanian dinars, which, as you probably know, correspond to about $2.1 million. And we are going to, we have started writing the specification for the vacuum undulator, which have been developed by Hossein Khosrowabadi from Sesame, he's Iranian, together with Hamed Taravnet, who works in Max 4, but is Jordanian. I was with Sesame in the beginning, now I moved to Sesame. So the two together have designed the vacuum undulator, which will have a very short period of 18.5 millimeters, so it's less than 2 centimeter period. And because of that, you have to close, as I said, you have to close the gap a lot. I remind you that we wrote a formula which says that K is equal to 0.9 times the field in Tesla times the period. So if you want an undulator, so you want this number to be between 1 and 2. So that basically means that the magnetic gap has to be of the order of the period or less, given the fact that you cannot have a magnetic field much stronger than the magnetic field is of the order of 1 Tesla or less. Therefore, we're going to have a minimum magnetic gap of 5.3 millimeters, which corresponds to a physical gap of 5 millimeters. That is the maximum we could. In principle, you would like to close it a bit more, but then you want the electrons to go through the device. So this was somehow a compromise which we had to agree with the accelerator physicist. Anyway, with a gap of 5.3 millimeters, magnetic gap, this is kind of performance we expect with first, third, fifth, seventh, ninth, and 11th harmonics. So we are basically going 1, 3. We basically are going to have the fifth harmonic centered around 10 or 12 keV, which is what you need to do macromolecular crystallography. So this is the calculated brilliance, which would put us exactly in the map of good, well-performing macromolecular crystallography beamlines in the world. Some discussion is going on about the remaining phase 1 beamline. So take this this type of beamlines with a larger margin, because we're discussing what kind of beamlines we will have, also depending on the possible future funding opportunities. There are discussions about Germany being interested in investing money for beamline at Sesame. There is an almost sure call for a European project for a European beamline at Sesame, and we know already how much money we should be able to get from that, which is 6 million euros. So depending on how these things converge and what is the interest of our partners in Europe and elsewhere. I'm stressing Europe because really Europe is helping us a lot. You may have noticed that the European Union by itself is one of the servers of Sesame, and indeed during the opening ceremony, which was in the second half of May, the European Commissioner for Research came to witness the interest of the European Union for Sesame. Because two beamlines will be ready this year, we were hoping to be a bit faster. I will be very frank with you, but we faced some difficulties during the installation. Anyway, we opened a call for proposals, which we call 0 because it's an experimental one. That was opened in December last year and closed in March this year. It is we got for free from Elettra, which happens to be the laboratory I come from, the so-called VUO, which is the Virtual Unified Office. So it's a portal which in the Sesame version is called Sesame User Portal. The address is sup.sesame.org.jo. And you can have a look at it and register as prospective users. And this is the system we have to handle proposals. So that was open, people applied, people registered, and they submitted proposals. This is the situation of the proposals which we received. We received 55 proposals for the 2 beam lines. Here you see the details. And you see also a breakdown in terms of nationalities, where nationality in this case indicate the nationality of the institution the person belongs to. So a Palestinian, for example, working in Italy would be counted as Italy in this. That is not such a case, but just to tell you what the country refers to. It's not the nationality of the person. So this is the situation. We have a lot of, most proposals are coming from Sesame members. As you can see, a lot are coming from Turkey, Pakistan, Egypt, some from Jordan, one from the Palestinian Authority, one from Sweden, one from Colombia, but that is in Italian, so. And one from France. Okay, so this is the couple from Italy. So that's the situation, and so we are going to organize or participate to meetings to address the less present user community from members, and my presence here has also this goal to make it, please do apply. By the way, we do have funds to support, if the proposal is going to be judged only on scientific merit. So we don't care about nationalities and things like that. If it is approved by the scientific committee, which I'm going to show you in a minute, then we have funds to support stays, because we have an agreement with an American private foundation, the Lounsbury Foundation, which is explicitly, they gave us funds explicitly to address the issue of supporting users from the members of Sesame. Some other members can use other type of supports. For example, some of the members in Sesame are, one is in the European Union, others are associated countries of Europe, and we are in a European project which will support them. Okay. Yes. You go there, you write a scientific proposal. You have to register, there are a few questions, who are you? Then you have to, there is a CAPTCHA, which is like in normal to say, then you receive an email to activate your account, and then it's very clear actually. If you ask questions, just contact us. By the way, we are soon going to have a person hired to handle the user office. It took us more than expected to find a person, but finally we found the person. She will start being trained at Electra next week, inshallah. And I'm saying inshallah because, the person is there, everybody is willing to start this thing, but there is some bureaucracy to be done. So we'll see. Anyway, this is the proposal review panel, or proposal review committee. As you can see, it's totally external from the from Sesame and the Sesame members. We have the chair of the committee, Samar Hasnain from Liverpool. He was before in the Sesame Scientific Advisory Committee, so he knows Sesame, and he was involved also in helping Sesame with donations from UK. Then we basically have 6 people, 3 with expertise in XRF or XAFS XRF, and 3 with expertise in infrared. And I've basically formed this list with them, which was then approved by the director of Sesame. It was discussed with some people. After I brought this list, which was based only on scientific achievements and some distribution nationality, I realized that we managed to reach a perfect gender balance, which is something which I like very much. Proposals have been given to them and are under evaluation. The access to Sesame is, we have a sort of we have a user organization which is called SUK. That's the way I call it. And people ask me, do you know what SUK means in Arab? Yes, I know. I know. So the SUK is the Sesame User Committee, and which is, I just copy-pasted the beginning of the terms of reference document of the SUK. And the idea is that you have 1 representative per member, and the idea is that they are collecting the needs of the user community from their member and refer to and convey them to Sesame. They're also giving their advice for the user meeting, which is every year, basically. And of course, since I'm here, I'm just telling you who is the Palestinian representative in this committee is Jamal Afif Gabon from the Bethlehem University. First time, just to tell you how, what was the selection procedure. The first time we had a preliminary version of the SUK, which was called something else, I don't remember how, which was, the user community was still under development, were identified by the people from the various members we knew. So then they were confirmed as SUK members. Their term, I don't remember exactly, I think they have 2 years terms, and then they are supposed to be elected by a local committee, which is handled by the individual members. So Sesame doesn't enter into it. Open Sesame. You don't expect to have Sesame as a name and don't have an Open Sesame as an initiative. So Open Sesame is a European project now running. It's already running since the beginning of the year, where various European institutions and Sesame work together for training needs of Sesame. So you see the various components. This is a Gantt chart or pseudo Gantt chart or call it whatever, time development of the various work packages. So we have a management work package which is handled by the coordinator, which is ESRF, European Synchronization Facility. Then a second work package is to train Sesame staff, and that is composed basically of visits of Sesame staff to European laboratories and of visits of experts from European laboratories to Sesame. So for example, as we speak, Mahmoud Abdelatif is at ALBA, the Spanish facility. Jihan went 1 month ago to Soleil, and she is going again to Soleil in October. We had various visits at Sesame. One is going to be a start in 10 days from now, and that would be an expert from Elettra, the Italian synchrotron, about RF cavities, with visits from AMBA and so on and so forth. What is very interesting for you is this, Work Package 3. Work Package 3, which is something I explicitly wanted, because the call, the European call, if you read it, includes only this and this. I said that this was essential. So we have included a work package which is meant for training of the prospective users, which is you, for example. And that is done with a number of actions. One is bursaries, that is coordinated by ALBA, the Spanish synchrotron. One is for bursaries for young researchers and for young students, actually, at the master or PhD level, from the region, so from the Sesame members, to go to European labs. Unfortunately, the first deadline was 1 week ago, but there will be a next deadline, I guess, next year, if I remember correctly. Yes, there it is. So there will be another one next year. So with that, we have some money to help young students from the region to go there. We have also a number of schools, thematic schools, which we're going to organize in the various Sesame members. The first school is going to be autumn this year. It will be about cultural heritage. It will be organized by the CNRS group. The CNRS is a French institution working at Soleil on cultural heritage, and it will be organized in Cyprus. Then there will be one next year organized by the Italian INFN for synchrotron and life science. Then there will be one on structural biology and one on energy materials. There's we have support from IAEA. Have a look at our website, and then you will find out call for proposals again for young scientists to go to other labs. ICTP is also offering various training schemes. And so there are a number of issues, so please get in touch with us to see what could fit your ideas if you want to be to go and be trained elsewhere. This was in 2014. It has been renewed. Year by year. So there will be fellowships also next year for training in infrared. So get in touch either with me or with Xian. The International Center for Theoretical Physics is actually supporting the infrared activities at Sesame. So to conclude, there are certainly challenges in Sesame. For example, the contribution from members are not as regular as one would like. So sometimes you have to slow down because of cash flow problem. But I think I've convinced you that things are actually going on, and soon. Oh, by the way, I didn't mention the most important thing. The ring reached its specified energy. So we circulated beams at 2.5 GeV, so that is working. The beam lines are going to be soon connected to the ring, and so, as I said, in October or November, you will hear about the first results from us. And if you have questions, curiosities, things, contact me, and I will be glad to answer or to forward your request to the appropriate person. Thank you for your attention.
Okay, before the break, we have a couple of minutes for questions for Giorgio. Any kind on all 4 lectures on Sesame?
Okay, we have, let's see. These things here are LED shielding, basically. And then we have, on the other side, you can see here doors, which you can use to access, which are fully interlocked with all the radiation safety systems. So you cannot open the door if there is a beam. Moreover, there are a number of monitors around to make sure that the radiation level is actually low. We don't have enough statistics on Sesame yet, but what I can tell you is that in laboratories like Elettra, we have a similar machine, similar shielding, and the radiation level in the experimental hall is lower than the natural background, because the natural background is shielded by the roof, so it's absolutely safe.
Any other questions? Okay, if not, thanks Giorgio for the wonderful lecture. And we now have a break, and we'll reconvene at noon for the closing ceremony. Please, if you haven't filled up the evaluation form, do it. It's really important that we know what you think, and it's really important that you are honest. Okay? So if there is something that you didn't like, please write it down.
Ah, thank you, thank you.
I printed out in 2 copies.
I should not. passport, the first thing I do is I pick up the phone and call my friend, my policeman friend. He helps me. Hey, what you doing here? Yes. If I want to go to a doctor, I call another doctor and ask him, what do you think of this doctor? That's what it was. Why do you know that? So I think that, yes.
والله ما شفت شيء بروجرام خلوا لي اعدلوا عليه شويه بس والله من هيك كانوا بيرجعوا 12 يعني لا بس بروحوا 12 في كان الاسبوع 12 مو يعني 12 ولا ترجع انت كان يعطيك شهاده ويكونوا مع الحضور وهيك
Last lecture live, Virgil, I'm sorry. Sorry? I think we may have forgotten to broadcast your last lecture. I'm sorry.
I don't know, there was something.
Was it working?
I don't know whether it was
Whether it was working or not? Yeah, okay.
I can certainly show the images of what I was projecting appearing there, but whether they were
live or not, okay, we'll see. Possible image.
Do you have any way of knowing people watch?
Yeah, actually, it shows you how many people are connected.
At a given time?
Yeah.
Oh, right.
So typically it has been about 2 or 3 for each lecture, actually. Typically at least one from Gaza. There's a group from Gaza. Typically at least one of them is watching, and there have been 2 or 3 other names that I don't know. Yeah. So people are,
But Arab names?
Yeah, Arab names, that's right, yeah. The number of views is much higher. Like you can see, I think people who just click on it for a little bit and watch like 2 or 3 minutes.
But then you can't
I can't tell them they're watching. But that has been order of 50 for most of the lectures, actually. So, yeah, it's higher than expected, to be honest. I thought this was just a thing they were doing publicity, but if people are actually getting science out of it, it's great. Yeah.
In this book, the Royal Institution, at the end of last year, they have a YouTube channel. So that's got almost 250,000 views. Wow. The Australian content. Wow. Or with a comment thread that's really just nasty or bonkers.
Really? How is quantum field theory so controversial?
No, religious things, not religious things.
Religious things?
Yeah, I just got an email from someone today who did just talk saying Jordan from Paul.
So what?
Jordan from Paul's apostle, blah blah blah. Lots of matters like this. But I think
it may well be, it was hard enough to extract it. Possible that it is, I don't know. Interesting, very interesting. Yeah. That's very interesting. Well, this is not bad at all. That's pretty good, even on celebrity, even on like...
True or not? Yeah.
No,
I gave 3 talks in Portugal last weekend. Oh, that was about 3 weeks ago. But I assumed, firstly, actually it's quite good. I did 3 proposals for question and answer sessions. In one of them, I assumed what a proton was. One of the very women architects, I don't know what a proton is. Like,
I think everyone who goes to school can know what yeah, no, it's true. It's completely useless knowledge.
French.
feel what? I feel like I do deserve it because okay, let me put it. I know the answer, but the thing is, the thing between you, really. So don't worry about it. Okay, we give
There are many ways to participate in this group. So don't take more of the time you're good. Just relax. I'm sure I'm fantastic telling you that.
Do we have